talking about acceleration of something. Acceleration of unsteady PDE Constrained Optimization in PETSC under PETSC.
Hi, so I'm working at Argonne, and despite the first word in the title, which is acceleration, this is not a computer science talk. Quite the opposite. It's a bit more mathy and overviewish, and I'm trying to kind of sell to everybody PDE Constrained Optimization as a study topic that is of relevance for HPC, the HPC community as well, and not only math and CFD or other applications. So, motivation. Why would it even be important? So, this figure here is simulation from Argonne, a different code than PETSC, an application code, NET 5000, if you ever heard of it. PDE Constrained Optimization means that you can solve for any sort of objective function you may have. You would like to minimize drag. You would like to fit parameters to certain final conditions. You would like to handle the acoustic pressure in a different way. All these are different areas of research, but the math, the underlying math is the same for all of them. So inverse problems, in the end, is a PDE constraint optimization that you're solving. If you want to find initial conditions or forcing, it's the same. Shape or mesh optimization, the math is also similar there. So it's a pretty big field. And now, what does it actually mean compared to, you know, you have the optimization part and PDE constraints. So how do these two go together? So a typical optimization problem is the one here: minimize some objective function given by some function f, and you have some constraint g. Now when you do PDE constraint optimization, the constraint is some PDE. So here, by this round P, I mean whatever spatial part you have. It can be the right-hand side in Navier-Stokes or whatever. And now your objective function becomes a functional. It's not a function anymore, which means that it's some sort of integral will take one point value, will not be, is not a field or anything of that sort. What this particular objective function says here is functional, is that I'm trying to fit my velocity, let's say, to some desired UD velocity at a certain time t. So the common way of trying to solve this is that you're setting up the Lagrangian multipliers problem. So you're rewriting everything in this way: objective minus adjoint times, and this times is not really times, would be a regular product within the optimization community. However, in PDE constraint optimization ends up being some sort of inner product. And this inner product for the spatial part is given as this, and for the time part is given as this. So the only thing you have to do when you set this up is make sure that you are dimensionally consistent. So if your objective function here, for example, has no time, it means that has to be at time t, and this guy you also have to integrate over time. So you should have the same amount of integrals in the same places, otherwise it's not going to work, obviously, because the Lagrangian in the end has to be a constant value. So you set this up, and now if we plug in what we actually had as an example for an objective function, it's going to be something of this sort. So no, this is the objective here, and this will be the PDE. And you're now trying to solve this as an unconstrained optimization problem, which means that you're just going to request, in order to find the minimum or maximum or whatever, you're just going to request that this equals 0. And there are two ways of going about it. One is continuous, and the other one is discrete. Probably a lot of you already know about this. Sadly, the two, continuous and discrete, they do not have a unified mathematical framework. You cannot write it in the same way. We try to do that to have like a nicer API in PETSC, but it's hopeless. They're two completely different worlds, and I will show you why in the next slides. So the derivations are different. And though for linear operators, which are the nicest always, it happens that they are identical. But that's a very special case, so you cannot generalize that. Okay, so now I'm just going to show you first what it means to take these derivatives, what kind of problem you end up with, and then show you continuous and discrete one after the other. So if you're saying that you want the gradient of the Lagrangian to be 0, that actually means that this Lagrangian depends on 3 variables. One is the direct velocity, the the variable of your initial PDE, v is the adjoint variable, and p is some parameter you want to optimize for. It means that you need to take all those three derivatives to be 0. And now you end up with something of this sort. And now this is not exactly correct. If you would write it discretely, this would have a transpose here, and you would have the discrete inner product in there. But I'm just trying to kind of show you what it looks like. So this is a system of 3 equations now. And each one of these equations is actually of the size of your PDE. And even worse, if you're doing unsteady PDE, each one of them, so like this on top there, for example, it's of the size of your PDE times the number of time steps you're supposed to take till you get to wherever desired location where you're trying to fit the parameter or whatever. So this problem is really big. So I can try and solve it via full space, whatever the optimization people call full space method. So, or all at once, or well, there are various names for that, or the KKT conditions. These are also known as the KKT conditions. So I can solve this all at once, and I will just have one system. But the size is, basically it means I stacked up all the time steps and the entire space and everything. So it's just humongous. And that's not the only problem, but it's also, it's very hard to tell how should I precondition this. If I have a PDE, I kind of know how to precondition my PDE, but I don't really know how to precondition the entire thing. So that can be an issue unless I have some pre-knowledge and I can solve it. But I can do another thing, which means, well, the stupid substitution. It's a 3 by 3, these are like 3 blocks. It's a 3 by 3 blocks system, and I can do a substitution, and then I solve something called the reduced space, in the reduced space sense. So I decouple these guys, and now each one of these equations is of the size of my original PDE, which I know how to handle. And well, when it comes to these two approaches, one is preferred by the optimization community because they're used to just solve some algebra. The reduced space, however, is preferred by the applications people because they just have one code to work with, and they would like to just run their PDE back and forth as they please, preconditioned as is. Now, just to show you exactly how this reduced space works in practice, so I was showing the scalar products and whatnot, and well, a nonlinear operator happens to commute like this, and well, there's just a lot of math there. But the continuous adjoint is actually far more intuitive and helps you understand the process and how the optimization loop actually works. So you just have to believe me that this will be the gradient with respect to u of a given Lagrangian. And what you would have to solve is forward in time your initial PDE, find some initial conditions here to go backward in time with some other PDE in the adjoint variable, and when you get to the end, update using some optimization tool, which of course we use TAO for this, have an update here and continue. So you have to do this back and forth till you actually converged. And well, you can already see this is insanely expensive, and every tiny, tiny improvement you can bring to solving your forward PDE or the backward one, it's going to be humongous given the amount of time steps and optimization loops you may have to go through. Now, okay, when it comes to the discrete one, and this is the one that is implemented in PETSC actually, there's also a continuous version. So the math looks completely different. So now I'm switching, now I have this u over line, which means it's a discrete variable. And this is kind of like how a time step would look like. I update my solution based on some whatever coefficients given by some tableau, whatever, and depending on the spatial discretization. And it gets incredibly ugly. I would do the same sort of thing, taking derivatives of the Lagrangian. The point is that I will end up with a formulation like this eventually. So when I have the gradient of my objective functional plus something equals 0. And this is actually the equation I need to solve. This dj at du0 is going to give me the update rule at the end of one optimization loop. So what I'm trying to say with this is that no matter how I'm trying to solve the discrete adjoint, I will always need a Jacobian. This will end up being a Jacobian if I start doing the implicit function theorem and a few other things. These terms here are going to be very well behaved. They're already coded in PETSC by Hongzhang, the other Hongzhang. But this is something that I need to input. And this is the Jacobian. So it's not like people usually think that, oh, I'm going to do an explicit method. I don't need the Jacobian. I'm fine. I don't need to compute that. But here, you cannot get away when you do discrete adjoints without computing the Jacobian by virtue of the mathematical derivation. So to conclude, what are the challenges? Probably some of them are already obvious. It's a very big problem that takes m iterations and time steps and whatnot. And you have to solve it twice and so on. Every single flop matters. So doing incremental improvements to your PDE is not useless. It's very data intensive for nonlinear problems. And I didn't get to specify earlier, actually. When you do this loop, if your problem is nonlinear, you're going to have a dependency of the backward on the forward, which means that every single step you took in the forward, you're going to need as you go backward. So if I'm somewhere here, solving this PDE, I'm somewhere here, I will need a corresponding U from the forward. And that is a bit of a tricky thing. It's being solved optimally using the revolve algorithm. I'm not addressing that at all. I'm just looking at how to solve this in the what are the best choices I can make to solve this the fastest. These are also very hard problem for chaotic dynamical systems, if not even unsolvable. And yeah, that's about it. And now going to the best choices. So let's say I take a two-dimensional Burger's equation. It's nonlinear, has 2 degrees of freedom, it's two-dimensional, as I was saying. It has all sorts of flavors of operators, some Laplacian, some gradient. So it's a suitable problem to showcase what are the best choices. So being two-dimensional, then I can use a tensor product representation, which I will show for the ones that are, probably some of you are already familiar, but I will just have a reminder. You should have a matrix-free implementation, and that is also because if you don't have a matrix-free implementation, and let's say you solve explicitly your forward, and on the backward you will have to do multiplications with that Jacobian, your backward is going to be much, much more expensive than the forward. So you lose a lot of time uselessly. The choice, what I'm trying to advocate here is that the choice of solution for this should be the spectral element method, because it has the highest accuracy per grid point. And I've seen that spectral element methods are becoming more and more popular lately. They weren't so much up to like 5 to 10 years ago. So probably a lot of you already know about SEM. And if you have long time horizons, you should solve this definitely using a reduced space method. It's not even possible the way the optimizers do it. So now talking about SEM a little bit. So SEM is very simple. SEM is kind of like high-order finite elements, only that you do it on a Gauss type of grid to avoid Runge's phenomenon. So if you have an FEM code, you can easily change it by just changing per element the representation. And SEM is becoming a favorite among HPC people because, as you can see in this is a typical, let's say, section of a mesh in SEM. Since now I can go extremely high polynomial order, it means that the ratio of computation per communication is going to be in the favor of scalability, because I can put like a lot of points inside and communicate very little on the edges. So, however, scalability does not mean that your time to solution is good enough. There's no guarantee for that. And when it comes to SEM, it's actually even so that it's not, because you're going to be very scalable by packing up every element with grid points. However, your time step is going to become very, very small because it does not scale in the same way as for regular problems on equidistant grids. So you will still lose. And I'm asking here the question, why isn't it a default if SEM is so great? Why isn't everybody doing SEM? Well, There are certain problems that are very suitable for SEM. However, in the CFD community, for example, you cannot deal with inverse boundaries, level set. They're not very well developed. Everything that is classical for finite elements, differences, and finite volumes, and so on, is not easily translatable to SEM. So, talking about the magic of tensor products, I was mentioning earlier that that's the way to go. And probably this is the most important point I'm trying to make here. One should never build a matrix. I know that that's the PETSC business. However, in this particular case, will be extremely expensive. So the way we're approaching this now is doing everything matrix-free and taking advantage of tensor products. And so here, if you see, I'm using the boldface notation for a data field that has all three components, let's say, if it's in 3D. And I'm using the regular, not boldface, for an array that has been unrolled. So now it's like you want one, you want two. So I went over every direction and I unrolled it. So doing this with tensor products, I'm just doing a few small matrix products instead of a big matrix vector product. And things become a bit nasty as you do nonlinear problems, variable coefficients, and the whole shebang that is needed for a full CFD code. However, it is doable in the end. Computing the Jacobian matrix-free is not that difficult. And I will just show you how it looks like. I know it will be quite a pain. So this is the forward PDE discretized. This is the Jacobian. I'm not even writing explicitly these terms anymore. They're the ones there. And it will end up being, in matrix-free form, something of this sort. And now if I will do variable coefficients, will be much, much worse. So we implemented this with MathShell in PETSC. The Kronecker products are implemented. Okay, Kronecker and tensor products are the same thing. Kronecker products are implemented with blast calls on dense block matrices. And forward and backward will end up being almost of the same, will have the same efficiency because it's all done the same. So we could try to improve this to have a easier way of computing the Jacobian. I was saying that it's not that hard. Well, okay, it's not that hard because I like doing this sort of stuff, but probably for a user that would like to be done within half a day and not 2 weeks, it is a bit more complicated. So the idea to save that would be to do automatic differentiation, of course. And I'm saying here, well, attempt 2.83 because I know there have been several attempts. Hovland was here yesterday. He's been doing this ADIC, AD4, and so on. He worked before with source transformation. What we're doing now is overloading. So this seems to be much better and much more flexible. However, one needs to be careful when one does it. You need to unwrap everything in PETSC to have access to your data and not do it on top of PETSC calls because that would be quite a nightmare. So yeah, that's my point. Oh no, results, I have results. Anyway, just some plots. Well, we did code this. It was not just math and well, it worked. There is some convergence. Everything goes down as it should. Iterations 18, error 10 to minus 14. After 18 iterations, and this is kind of how the gradient looks like. It's not, it's quite a wiggly, nasty guy. And there are many mathematical issues to solve, but I'm just not getting into those. That was my point. I already made my conclusions on the way, so I will abstain from. Oops. So TAO is just used in the part. So in the optimization loop, I don't know if I can go back that much. Yeah, so in the optimization loop, TAO is needed in this part. in actually doing the update, computing based on the gradient, computing how to go further and have a better, let's say, guess for the next optimization loop. Oh, yeah, LMVM is the standard. Yeah, no, so we didn't do any study yet. So the plan we have is to couple TAO with NEC 5000, which is the code I was working on before, and do it on a full CFD application, rather than study it on a PET problem. If you have a small problem, you're just going to get incremental differences, and you cannot really tell whether really, this took 18 iterations. If I compare two methods and one is 18 iterations and the other one 17, I cannot say much about it. So the bigger the problem, the differences are bigger, so I can make stronger statements. That's why I would like to have bigger cases.
So in your case, you're a bit sorry.
So when you're doing, if you've got a finite element code, including spectral element code, and what you're trying to do is automatically get the Jacobians by differentiating the implementation, I would claim that, that is hard. That's why AD is a really hard problem. And basically because you're doing it at the wrong point. You should differentiate the forms automatically before you produce the
So it's done by overloading. It's not me, it's Michelle Shannon. I should have mentioned his name. I'm sorry for skipping it. I only had one slide. I was not planning to talk too much about it. We're doing it by overloading, and it's quite neat, and it works. So he can differentiate even my blast calls for all the tensor products and all that. So you just have to be careful that you provide something that is, you only provide operations on the naked data and not instead of doing like a matmult in matmult or whatever it is in PETSC, you just do your own mat. You go from global to local and you do it in local. And then that part, those operations is going to overload. So I'm going to have my own routine RHS function, let's say, that does that, and he's going to come on top and do the AD part on it.
Yeah, so now you have to write your one and he had to AD that. So this is what UFL is for.
I'm sorry?
This is what UFL is for. So you use Phoenix or Phydrake, you write the wig form.
Right.
And now you can differentiate the wig form before you generate the code that does that. So the thing that you differentiate is the symbolic bit. And then you generate the code for the differentiated version and the original version, and now it's much easier. And you'll get faster code in all probability because differentiating through the implementation is really hard.
Okay, I'm not an AD person, so I cannot. I just know that we actually did it and it works and it's okay for a small problem, but I cannot vouch for.
And David, you're lucky. You work with applications that know what their equations are.
Well, but this is, all of this is just...
Yeah, in PDEs, you also know what your equation is.
Right, so I did preface this by saying, like, you're doing a finite element problem, right? So specifically, if you're doing a finite element problem, we know how to do this in a much easier way. I agree, if what you're doing is not a finite element problem, then, you have to deal with a pit of AD, which is, and it's not a pit of AD because the people who do it are doing it wrong or dumb or anything like that. The people who do it are very, very smart, but they are trying to solve a very, very hard problem because they are reasoning about code expressed at a very low level, which is hard. What you want to do is reason about code expressed at a very high level because that's easy.
Well, I wanted to ask about part of the nuance of predictive performance. So the spectral elements does in asymptotically have high efficiency per flop, but sometimes it can be mitigated by the fact that burgers support shocks. If you get a shock, you're going down to first order accuracy rather than
We did an error analysis, so you can do. Okay, so for SEM you're never going to have like a nice line. It doesn't have algebraic. It has spectral convergence. So you need to go in spectral space and look at the coefficients and their decay, and then from there say what your loss is. So yes, true. The sharper the gradient, the lower the accuracy. That is a fact. When it comes to shock capturing, yes, spectral element method is not totally suitable. There are people that do a few things. You guys, I think, do a little bit when it comes to shock capturing, but it's not a done problem. So the most you can do is kind of like have it sharp, and you can actually push it quite a bit. For like polynomial order 8, you can have it pretty sharp.
I don't want to move us away from asymptotic, ineffective arguments about performance toward measuring the error and measuring the flops and plotting it, and saying, what kind of error can I get for how many flops and compare them? Because that's a purely empirical thing, and we don't do it.
What do you mean it's purely empirical?
I mean, I can just measure it. I don't have to have a theory. I can have a theory after the fact.
Right. Yes, you can take any sort of sine-cosine combination, and it will be a fact that you will see it in a plot that the error of SEM is far lower than for finite volumes or anything else. Okay, maybe I misunderstood what you asked. I'm not sure. Yeah.
Lawrence?
I have a very simple question. So, at the beginning you said, and I agree very much, that you need to know about the right, using the right inner products. So, and then in your optimization you're using TAO. Does TAO know about the right inner products?
If you tell it to, yes. So I mean, so what will end up being is, in the discrete sense, the inner product will end up being V transpose mass matrix U. I mean, you will have a mass matrix, or you will have the integration weights corresponding to that inner product. And yes, one needs to take that into account in the way it's being.
And so if I use TAO and I'm telling about how to get the least representative of the dual, all the algorithms work correctly?
So the only thing you give tau is the gradient. You do your entire PDE part, you do it by yourself in PETSC, with PETSC time steppers, let's say, or not. Or tau only wants the gradient when you're done. The gradient and the objective function on how much is the objective, to figure out when to stop.
Representative is used like in an MPN. You just input a gradient in your space, and then the representative is computed by the MPN.
But if
by solving for the
coefficients in spaces, like
the Reese representative of math matrix is like you're trying to get the